Hello, and welcome to next lecture of the parallel programming and system design. So, up until now, we have studied a very basic fundamental of the parallel system architecture. Now, what we're going to go into more details about what are the level of the hardware level parallelism and what are the fundamental building blocks to achieve the parallelism. So, with that, let's see what are the hardware level parallelism. So, first of all, you can achieve the hardware level parallelism in the first way, which is a shared memory. So what you see here is a shared memory. It's easy to program, but there is a risk of contention. So if you see the example of a shared memory, it could be like you may have a multi-core CPU. It has a RAM. So the same memory is shared across multiple cores, which is a shared memory system. Now, the another level of hardware level parallelism is used is a distributed memory. Distributed memory means it's a cluster. So now what happens when it's a distributed memory? That it scales much better than a shared memory, but it requires explicit communication. Like you need to distribute your work, you need to distribute your tasks. So distribute your tasks, work. You need to have an explicit communication. So, for example, there are available protocols such as MPI, which is nothing but a message passing interface. So, these are the system for shared memory and distributed memory. Now, what could be the next way? Next way would be that you have a hybrid mechanism. Hybrid mechanism is nothing but you can call it out as a heterogeneous. So in this heterogeneous computing example, you have a combination of a CPU and a GPU. Now, when you see here, the instruction pipelines and the fundamental building blocks of the both architecture are very, very different. And when you are clubbing both together, when your program runs on both of these, that is called a heterogeneous computing. Let's take an example. So if you are running a program where you say line 1, 2, 3, 4, 5, and 6, let's say your program divided into the 6 lines. And if you're trying to recall that you will run onto shared memory, so eventually you will try to fit the maximum of your program and your work, which is driven by a program, into the one shared memory. And the execution can be done by multiple core. Take an example that every of the line is a different function, and each function is executed by a different cores. It could be that this is picked by core one, this is picked by core two, this is again picked by core one, core two, and maybe core three. So this could be the example of a multi-core, and the shared memory would be used where each core will share the same memory. However, in case of a distributed system, a cluster, this code, you can assume it is a different machine. So you need to explicitly program the machine. So if you are running just on machine one, then you need to make sure that you are efficiently distributing all the tasks and you are passing the instruction to distribute the data and collect the result back also. So this definitely includes the overhead of running on a different machine and the data communication. Now, one more example you would say is a heterogeneous computing. Now, how that differs is that, for example, you say that this line of code is working on a CPU However, there is the next few lines of code which may run on a GPU, and you may recollect the result back on the CPU, and you can finish your program. Or it can have a multiple functions in order. But eventually, in the gist, if you see, in a single program, few code blocks will be executing on the GPU, few code blocks will be executing on the CPU, which is known as a heterogeneous computing, or you can say the hybrid level of parallelism. Now, up until now, you should have a question like, why would you choose a GPU over a distributed cluster? Now, if you have ever read anywhere, GPU is a much faster than a CPU. And why would you like to choose GPU over a distributed cluster? So, take an example. If you have a task which has the same instruction, but you have a same repeated data when you need to proceed with the same arithmetic calculations, which is nothing but a data level parallelism. In that case, you will opt to choose GPU over the distributed cluster. However, if your system has requirement of handling a different instruction, different task in its own, which may also depend on the various IO handling of workloads. In that case, distributed cluster may serve much better. So that's all for information from this module. In the next module, we'll try to cover more fundamental building blocks and how we would be focusing on implementing the parallelism.